Now, if you look through my YouTube videos, you will actually find a different version of this video. It looks radically different than what I'm about to talk about here. And this is actually an instance in my case where, as an instructor, I actually learned it wrong. And I've gone through now with this video to correct my mistake. So let's talk about the reaction coefficient Q, reaction quotient. Now, Q typically in books is not defined properly. And I say not defined properly in the sense that it's wrong. That's not how you define it. And my opinion, and this is very much my opinion, is that the reason it's taught the way it's taught is that it's easier than explaining to you what's really going on. So what is Q actually? Well, Q is unitless, and Q represents, well, is represented by the following expression. Q of the products, Q of the reactants, and it's the activity of species I raised to the reaction coefficient of I. So pi here represents the product. So you're probably familiar with the big sigma symbol, which means the summation. Pi is the equivalent for multiplication. So it's the activity of all the products raised to the reaction coefficients divided by the activities of all the reactants raised to their reaction coefficients multiplied together. So what is activity? Well, activity describes our concentration relative to some reference concentration. Now, this is a very overly simplified definition. There are far more complicated definitions, but I will put the comment in here. And once you start seeing the sections on fugacity, you'll understand why I'm kind of okay with not trying to explain this in full detail. Our activity of species I is defined as the concentration of I. So the concentration of whatever the compound is in molarity divided by a reference concentration. Now, how we define this reference concentration depends on the phase. So for gases and aqueous mixtures, because their concentrations can change so much, we're going to define the reference concentration as 1 molar. So for any gas or aqueous mixture, it's simply the concentration divided by 1 molar, or the concentration. But because the concentration is in molarity and the reference is in molarity, activity here doesn't have any units. Now, if we have a solid or liquid, we're going to define the reference concentration as the concentration of that material at 1 atmosphere in room temperature. Now, if you think about it, concentrations of solids and pure liquids don't change that much. You really have to radically change the temperatures and pressures to really get their concentrations to change, because it's a solid, right? Its shape doesn't, its number of atoms per unit volume doesn't change that much. So the concentration divided by the reference concentration basically puts the activity at 1, or unity. And so for solids and pure liquids, when we look at our expression for Q, our concentrations end up disappearing. So I have a video on how to quickly figure out how you do the concentrations, or how to work out what the expression for Q is based on a reaction. We'll talk about that next. But basically, because of how we set our definitions for activity and how we set our reference concentrations, the concentrations of the solids and liquids don't appear in this expression for Q, only the concentrations of the gases and the aqueous mixtures. And even those are actually unitless because they're being divided by 1 molar.